A thin river of starlight winds through the silent outskirts of the Milky Way, a faint arc, so delicate it almost disappears into the dark. This glowing thread is a stellar stream, the remnant of a small galaxy that once drifted too close to our own. Over billions of years, the Milky Way's gravity pulled it apart, stretching its stars into a ribbon that now wraps quietly around the halo. Each star still follows the path of its former home, moving in slow unison like dust caught in an unseen current. Though the galaxy that birthed them is gone, its memory lingers in their motion, a faint footprint preserved in the void. Far from the bright spiral arms, these streams drift, undisturbed, tracing the secrets of ancient mergers. Some are narrow and fragile, no wider than a few dozen light years. Others span half the sky, vast arcs of pale light, invisible to the human eye, but unmistakable to telescopes, mapping their slow, patient paths. They tell of long-forgotten encounters, collisions that reshaped the Milky Way's early form. When the universe was young, galaxies collided often, each impact leaving behind these subtle trails. Astronomers study the chemistry of the stars in these streams, reading their elements like lines of old cosmic handwriting. Stars born in dwarf galaxies carry different signatures than those formed in the Milky Way. Less metal, fewer heavy elements, a quieter composition shaped in simpler environments. By comparing these fingerprints, scientists trace each stream back to its origin, uncovering the lost galaxies that once drifted freely before being absorbed into our own. Some streams move high above the galactic plane, following strange tilted orbits that cut through the halo in long, looping arcs. Their paths are clues. They reveal how the Milky Way's dark matter halo is shaped, where it stretches, where it thickens, where it pulls with uneven strength. Invisible but immense, this halo guides their motion like a hand, shaping the flow of a river. By watching the stars drift, astronomers map what they cannot see. A few streams may be all that remains of galaxies older than the Milky Way itself. Their stars formed before our spiral arms existed, before the disk took shape, before our galaxy had a settled identity. Now they drift like ancient relics, suspended in the emptiness between stars, reminders of a time when the cosmos was more chaotic and galaxies were still learning their shape. If you could stand far outside the Milky Way and watch from a quiet distance, you would see these streams as ghostly threads wrapping around the spiral. Soft arcs, curving bands, trails of stars pulled into motion by encounters long past. They are not bright, they do not shout, but like the faded rings in a tree's trunk, they carry the memory of growth, slow, quiet, continuous. Even now, new streams are forming as small galaxies fall inward. Their stars begin to scatter, pulled into tidal arcs that will stretch for tens of thousands of light years. The Milky Way is still growing, still absorbing, still reshaping the sky around it. Nothing here is permanent. Not the spirals, not the orbits, not even the galaxies themselves. Only the motion remains, steady, patient, whispering across billions of years. Along the faint outer rim of the Milky Way, where the spiral arms begin to lose their structure and dissolve into darkness, lies a vast region filled with clouds colder than anything on Earth. These clouds are so frigid, so quiet, that their molecules move only slightly above absolute stillness. They are the Milky Way's molecular reservoirs, the silent basins from which future stars will someday rise. To the eye, they appear as empty pockets of blackness, erasing starlight like spilled ink across the sky. But hidden inside are the raw ingredients for creation, waiting for the slightest disturbance to awaken. These dense clouds, called giant molecular clouds, drift through the galaxy like slow-moving continents of gas. Some stretch for hundreds of light years, vast enough that billions of Earths could fit comfortably within them. Inside, the temperature hovers just a few degrees above absolute zero. Hydrogen molecules cluster together. Dust grains gather into fragile clumps. The outer layers remain soft and cold, while the inner cores grow denser, darker, more secretive. These regions are not illuminated, not warmed, not stirred. They simply wait in perfect stillness. But even the quietest cloud does not last forever. A passing shock wave from a nearby supernova can ripple through it, compressing the gas and folding the dust into tighter knots. A drifting magnetic field can bend the flow of molecules, subtly nudging the cloud into collapse. Even the pressure of surrounding gas can push it inward, one layer at a time. When the collapse begins, it grows slowly, a process not of days or centuries, but of millions of years. Gravity gathers the darkness into a shrinking sphere. The molecules fall inward. The dust thickens. Slowly, a core forms at the center. Only in these small, dense regions does heat begin to rise. What was once a silent cloud becomes a cradle. Pressure increases. Hydrogen atoms squeeze together. The core grows hot enough to glow faintly in infrared, invisible to human eyes, but unmistakable to telescopes tuned to that wavelength. At this stage, the cloud has not yet formed a star, but it has begun to dream of one. As the collapse deepens, a rotating disk forms around the growing protostar. Dust collects in swirls, gas spirals inward, jets of material shoot outward along the forming star's magnetic poles, carving narrow tunnels of emptiness through the surrounding cloud. These jets glow softly, illuminating the dark environment with a gentle radiance. They reveal the shape of the forming star, young, hot, and fiercely bright inside its dusty cocoon. Eventually, after millions of years, hydrogen fusion ignites. The protostar becomes a true star, sending out waves of heat and pressure that blow away the remaining gas. What was once a pitch-black void becomes a luminous nursery filled with newborn starlight. Some of the surrounding material forms planets. Some drifts back into the interstellar medium. Some escapes into the halo, carried on slow winds. Yet most molecular clouds do not reach this stage. They dissolve, evaporate, or are torn apart long before collapse begins. The galaxy contains countless such clouds, dark, untouched, unawakened. They float through the spiral arms like unfulfilled possibilities, shaping the rhythm of star formation without ever becoming stars themselves. These cold regions remind us that the Milky Way is not only made of brilliance, it is built from patience, from stillness, from quiet reservoirs of potential. Creation in the galaxy is not a constant blaze. It is a slow, delicate cycle shaped by shadows as much as by light. The inner regions of the Milky Way glow with a soft, golden haze, a warm concentration of ancient starlight that surrounds the galactic center like a luminous heart. This structure is the galactic bulge, a densely packed sphere of old stars whose ages stretch back almost to the beginning of the galaxy itself. From afar, the bulge would look like a glowing ember at the core of a spiral furnace. Yet up close, it becomes a labyrinth of drifting stars, tangled orbits, and quiet, ancient light. The stars in this region do not follow orderly, circular paths like the stars in the disk. Instead, they move in complex, elongated orbits, crisscrossing at every angle, weaving through one another like threads pulled tight through a knot. This chaotic flow creates a smooth, rounded glow, a kind of stellar fog made from countless tiny motions. Each star completes its orbit in a few million years, but because every orbit tilts and stretches differently, the entire region appears to swirl without any clear direction. The bulge is enriched with metals, not literal metals, but astronomical metals, meaning all elements heavier than hydrogen and helium. These elements were forged in ancient cycles of star formation and supernova, long before the spiral arms settled into their current shape. This richness suggests that the bulge formed quickly in an era when the galaxy's early stars were being created and destroyed at a rapid pace. Many of its stars are older than the sun by billions of years, their light softened by the long journey it has taken to reach the outer disk. At the very core lies something even stranger, a star population that rotates as a bar, stretching through the center like a thick beam of light. This bar structure funnels gas inward, pulling it along curved paths toward the center, where new stars occasionally ignite in short bursts of activity. Though the bulge is ancient, it is not completely still. Flows of gas, dust, and stars continue to move through it, shaped by gravity and time. Hidden deeper still, at the center of the bulge, is the Milky Way's supermassive black hole, Sagittarius A*. Its presence influences the motion of nearby stars, causing them to whip around the dark center at tremendous speeds. These stars orbit in tight loops only a few light days across, completing their entire circuits in mere years. Their motion offers the clearest proof that something immensely dense resides there, shaping the flow of the inner galaxy despite being invisible to the eye. But the influence of the black hole is limited to the very core. The larger bulge is shaped not by this central monster, but by the collective gravity of billions of stars. Their combined mass is so immense that it forms the gravitational spine of the entire Milky Way, anchoring the spiral arms and stabilizing the galaxy's rotation. Without the bulge's weight, the disk would warp and twist far more dramatically. Dust weaves through the bulge in dark streaks, forming narrow lanes that block light and create intricate patterns when viewed in infrared. These dust lanes trace the paths of gas flowing inward, marking routes that stretch toward the galactic core. Observations reveal that the bulge is not perfectly spherical. It is slightly peanut-shaped, a subtle distortion sculpted by the rotating bar at its center. This hidden geometry only becomes visible when astronomers map the light of millions of stars. If you could hover near the bulge and look outward, the Milky Way's disk would sweep around you like a vast, glowing ring. But if you turned your gaze inward, the light would thicken into a soft, golden fog. Stars would surround you in every direction, each one a whisper from the early universe, each one reminding you that the galaxy's center is not chaotic in noise, but in motion, a quiet storm of ancient starlight. Across the outer reaches of the Milky Way, faint arcs of hydrogen drift like unseen tides, forming immense, curling structures known as galactic chimneys. These openings, carved into the disk by ancient explosions, act as vents through which hot gas escapes into the halo. They are not visible to the human eye, but they reveal themselves through radio waves and soft X-ray glow, outlining tall, column-like cavities that stretch thousands of light years above the galactic plane. These chimneys begin with clusters of massive stars. Throughout their lifetimes, such stars generate intense stellar winds, streams of particles that blow outward at hundreds of kilometers per second. When several giants form close together, their winds overlap, merging into bubbles of hot, expanding gas. Over millions of years, these bubbles grow large enough to push aside surrounding material, sweeping dust and hydrogen into curved walls. The structure gradually elongates, piercing upward through the thinner layers of the disk. Then come the supernova. Each massive star ends in a violent explosion, injecting enormous energy into the cavity. The shock waves stack together, pressurizing the expanding bubble until it breaks through the top of the disk. When it does, the hot interior gas streams outward like smoke, rising through an open chimney, carrying enriched material into the galactic halo. This release stabilizes the region, preventing runaway star formation and allowing the disk to breathe. The walls of these chimneys glow faintly in ultraviolet light, shaped by the ionizing radiation of young stars. Inside, the gas is too hot and diffused to shine brightly in visible wavelengths, but in other frequencies, infrared, radio, X-ray, the structure becomes clear. Filamentary dust outlines the edges. Magnetic fields bend along the walls, guiding particles upward. The whole system resembles a silent eruption frozen in time, stretching far above the spiral arms. Some galactic chimneys grow to extraordinary scales. They can span thousands of light years in height and hundreds in width, large enough to lift material from the disk into the halo. Once there, the gas cools gradually and may eventually fall back as part of the galaxy's long recycling cycle, raining down in small clumps that feed future star formation. In this way, chimneys serve as both exhaust and intake systems, releasing excess energy while returning cooled material to the disk. These vertical channels play a crucial role in regulating the galaxy's temperature. Without them, hot gas would build up inside the disk, increasing pressure and disrupting the delicate balance that allows stars to form. Instead, the chimneys act as vents, letting the Milky Way maintain a stable cycle of heating and cooling. They connect the bright, star-filled disk to the faint, spherical halo, creating bridges of hot gas that move between the two environments. Some chimneys originate near the Milky Way center, where star formation can occur in concentrated bursts. Others form along the spiral arms, carved by clusters that ignite in the dense regions of molecular clouds. Over time, old chimneys fade as gas dissipates, while new ones open elsewhere, creating a shifting network of vertical structures that reflect the galaxy's evolving energy. From the outside, if one could view the Milky Way in a wavelength sensitive to hot plasma, these chimneys would resemble flickering pillars rising from the disk, quiet monuments to ancient stellar activity. Inside them, winds and shock waves continue to flow softly, carrying whispers of former stars into the surrounding darkness. These towering cavities remind us that the Milky Way is not merely a flat whirl of stars. It is a breathing, circulating system, releasing energy, redistributing matter, and shaping its own future through structures carved by brilliant, short-lived giants. Far beyond the spiral arms, in the dim boundary where the Milky Way begins to blur into intergalactic space, lies a loose scattering of ancient stars suspended in a vast spherical shell. This region, known as the stellar halo, is not dense or bright. It is quiet, thinly populated, sparsely lit, and stretching outward for hundreds of thousands of light years. The halo forms the galaxy's faintest outskirts, a whisper of starlight surrounding the disk like frost on the edge of a window. The stars that drift here are unlike those in the spiral arms. Many are extremely old, formed when the universe was young and heavy elements were still rare. Their light is tinged with simplicity, carrying the chemical signature of an era before multiple generations of stars enriched the cosmos. These ancient travelers drift in slow, elongated orbits, moving in every direction rather than following the disk's orderly rotation. Their paths are scattered, looping, and unpredictable, a reminder that the halo was shaped by a history different from the structured evolution of the disk. Most of these stars were not born in the Milky Way. Instead, they arrived from smaller galaxies that merged with ours long ago. When these dwarf galaxies fell into the Milky Way's gravitational field, they were gradually pulled apart, their stars scattered into long arcs that wrapped around the galaxy. Over billions of years, those arcs dissolved into the halo, leaving behind a mix of stellar populations that carry the memory of long-lost galaxies. Each halo star is a fragment of a former world. Threaded through this spherical region are subtle streams, faint, elongated remnants of star clusters and dwarf galaxies torn into ribbons. Some streams remain tightly bound. Others have stretched into delicate curves spanning tens of thousands of light years. By tracing their motion, astronomers reconstruct the Milky Way's history of collisions, uncovering when and how certain galaxies were absorbed. The halo, in this sense, serves as a fossil record, every stream a silent chapter of the galaxy's ancient growth. Though the halo appears almost empty, it holds enormous significance. The majority of the Milky Way's dark matter, invisible, massive, and mysterious, resides here. Its gravitational influence shapes the orbits of halo stars, pulling them into paths that reveal the unseen mass surrounding them. By studying how these stars move, scientists map the distribution of dark matter, tracing the unseen skeleton that supports the galaxy. The halo also contains hot, diffuse gas, hydrogen, heated to millions of degrees. This gas forms a nearly invisible atmosphere around the galaxy, extending far beyond the regions where stars shine. It glows faintly in X-rays, evidence of ancient supernova whose shockwaves carried gas outward until it settled into this quiet, heated shell. Though too thin to see, this halo gas holds more mass than all the stars in the disk combined. Occasionally, cold gas clouds drift through the halo as well, high-velocity clouds moving at hundreds of kilometers per second. Some may be remnants of dwarf galaxies being absorbed, while others could be material returning to the disk after cooling in the halo. These clouds act as bridges in the galaxy's recycling cycle, carrying gas outward and then back inward over millions of years. If one could float far above the Milky Way and look toward the center, the halo would appear as a soft, spherical glow sprinkled with ancient points of light. The spiral arms inside would be bright and sharp, but beyond them, the view would fade into a gentle haze of old stars drifting in silence. These stars mark the limits of our galaxy's influence, forming a boundary where the pull of the Milky Way weakens and intergalactic space begins. The halo stands as the galaxy's oldest, quietest region, a vast archive of its past, faint but essential, shaped by forgotten collisions and held together by the invisible weight of dark matter. In the quiet darkness between the Milky Way's spiral arms, there exists a subtle population of stars that refuse to behave like the majority around them. While most stars follow the galaxy's rotation in orderly, circular paths, these particular stars drift in unexpected directions, some moving opposite the Milky Way's spin, others cutting across it at steep angles. They are known as retrograde stars, and their motions tell a story far older and more dramatic than their faint light suggests. Retrograde motion in a galaxy is not natural. It does not arise from the Milky Way's formation, nor from the normal evolution of its disk. Instead, it points toward an event, a disruption, a collision, a merger with a smaller galaxy whose stars carried their own spin. When that galaxy was drawn into the Milky Way's gravity, its stars were scattered and stretched, but their original motion survived. They continued to orbit backward, preserving the memory of the world they came from. Some retrograde stars are found high above the disk, in the halo where ancient populations drift on long, looping trajectories. Others lie hidden within the disk itself, moving silently against the grain of millions of fellow stars. Their presence inside the disk is a kind of cosmic fingerprint, evidence of past mergers that were so thorough, so well mixed, that their remnants are now woven into the structure of the Milky Way itself. One of the most significant clues comes from a sprawling population of retrograde stars, thought to be the remains of a long-lost dwarf galaxy that merged with the Milky Way billions of years ago. This ancient collision was powerful enough to reshape sections of the galactic disk, stirring stars into higher orbits and puffing the thin disk into its thicker, more diffuse counterpart. The retrograde stars left behind still trace the orbit of their parent galaxy, revealing the path of a merger that forever changed the Milky Way's structure. Retrograde clusters also exist, small, tight groups of stars that were once part of larger systems. These clusters orbit at odd angles, often on elongated paths that stretch deep into the halo before returning to the inner regions of the galaxy. Their chemical signatures differ from those of native Milky Way stars, carrying fewer heavy elements and marking them as outsiders that arrived in a quieter, earlier universe. Even the motion of local stars near the sun bears the imprint of retrograde debris. Some stars in our neighborhood travel against the galactic rotation, slipping past us like quiet travelers heading upstream. Their paths are not chaotic. They are remnants of long-ago structure preserved by gravity's persistence. Each one is a piece of a shattered galaxy carried through the Milky Way's vast currents. These retrograde populations help astronomers reconstruct the Milky Way's family tree. By mapping their orbits, measuring their chemistry, and tracing their distribution across the sky, scientists can identify the mergers that built the galaxy, when they occurred, how large the incoming galaxies were, and how deeply they seeded their stars into the Milky Way structure. In this way, retrograde motion becomes a form of cosmic archaeology. Over time, these stars will continue to drift through the galaxy, following their backward paths with quiet consistency. They do not slow, do not realign, do not dissolve into the rotation of the disk. Their trajectories are stable, locked in place by the gravity that governs all motion in the Milky Way. They serve as reminders that galaxies are not born in isolation. They grow by absorbing others, stitching together fragments of distant worlds until the past becomes indistinguishable from the present, except in the paths of a few silent stars moving against the flow. Threaded through the spiral arms of the Milky Way are narrow, elongated regions where stars are born in synchronized waves, as though guided by an unseen rhythm embedded in the galaxy's structure. These features are known as spurs and feathers, thin, branching extensions that split away from the main arms, winding into the empty spaces between them. They are subtle, almost delicate, but they play a vital role in shaping the distribution of star formation across the disk. spurs are strikingly linear. They emerge from the spiral arms like cosmic bridges, carrying gas and dust into the less crowded regions of the disk. Within these slender threads, star-forming material gathers in long chains. Massive stars ignite along them, spaced like lanterns illuminating a quiet path through the darkness. The iconic Orion Arm, the small spur that contains our sun, is one of these structures, an offshoot of a larger spiral that once guided the gas from which our solar system was born. Feathers, by contrast, resemble soft, curved wisps pulled gently from the spiral arms. They form when turbulence or gravitational forces shear the gas clouds, stretching them into feather-like arcs. Over time, these arcs drift between the arms, blending into the broader background of the disk. Feathers create subtle patterns in the Milky Way's dust lanes, forming dark streaks that weave their way across the glowing spiral, visible in infrared and radio light as faint tracings etched into the disk. Both spurs and feathers arise from instabilities within the galaxy's rotating structure. As gas flows along the spiral arms, it encounters regions of compression and shear. These forces stretch the material into thin threads, and once separated from the main arms, gravity shapes them into stable paths that maintain their form for millions of years. Along these paths, gas clouds collide more frequently, triggering bursts of star formation that illuminate the structures in ultraviolet and infrared light. Some spurs host chains of young, hot stars that outline their shapes like beads on a string. Others remain largely dark, containing cold gas that may eventually ignite, but has not yet reached the density required to collapse. These silent spurs act as reservoirs of potential, waiting for the right moment to awaken. Their shapes reveal the underlying dynamics of the disk, offering clues about how spiral arms influence the flow of matter. Feathers, on the other hand, often appear in groups, layered like the veins of a quill. The spacing between them reflects how gas responds to the spiral arm's gravitational pull, a natural pattern formed by compression waves moving through the disk. When viewed from above, they create a subtle texture across the Milky Way, a delicate layering that adds depth to the spiral pattern. Observations of other galaxies reveal similar structures, confirming that spurs and feathers are not random quirks, but fundamental features of spiral systems. In some galaxies, these extensions are so pronounced that they dominate the spaces between arms. In others, they appear faint and rare, shaped by differences in rotation, gas density, and the strength of the spiral pattern. The Milky Way contains dozens of these structures, but many remain unmapped because they blend into the brightness of the disk. Only with precise surveys can their outlines be traced, revealing a hidden complexity woven through the galaxy. Each spur and feather tells a quiet story of gas pulled into motion, of stars born in narrow corridors, of the subtle architecture that guides the Milky Way's slow evolution. They remind us that the galaxy is not a simple, symmetric spiral. It is a living structure filled with branching paths, drifting arcs, and delicate filaments shaped by gravity, turbulence, and time. The spaces between the arms are not empty. They are threaded with quiet patterns that reveal the galaxy's intricate design. Scattered across the Milky Way's disk are immense voids, hollow regions where gas is thin, stars are scarce, and the usual patterns of the galaxy appear strangely absent. These regions are known as superbubbles, vast cavities carved out by the combined force of multiple supernovae and the relentless winds of massive stars. Unlike the small, simple bubbles created by individual stars, superbubbles can stretch for hundreds, even thousands of light years, leaving behind enormous hollows in the galaxy's structure. Inside a superbubble, the gas is incredibly hot, millions of degrees, but also extraordinarily diffuse. The pressure from this heated interior keeps the bubble expanded, pushing against the surrounding medium like an invisible hand holding open a cavity in the interstellar material. Over time, the outer edges of a superbubble cool, forming thin shells of compressed gas. These shells are subtle but important. They become sites where clouds condense, where dust gathers, and where future star formation might eventually ignite after the region stabilizes. Many superbubbles begin in massive star clusters, when dozens of hot, short-lived giants form in close proximity. Their stellar winds interact and overlap, sweeping material aside. As the cluster evolves, several supernovae follow in rapid succession, each one adding to the expanding cavity, each one reinforcing the structure. The result is a hollowed-out region surrounded by a sculpted wall of denser gas. The sun itself lies inside such a structure, nestled within a local superbubble created by ancient explosions millions of years before the solar system formed. Some superbubbles grow large enough to merge with neighboring cavities, creating even grander interconnected voids. These networks weave through the disk like hidden tunnels, linking regions that otherwise appear isolated. Astronomers use radio and X-ray observations to trace their faint outlines, mapping their contoured edges and the hot gas flowing within them. Sometimes these cavities connect to vertical channels that vent material into the halo, galactic chimneys formed by the upward escape of superheated plasma. The boundaries of superbubbles often host intriguing phenomena. As the expanding shells sweep through the disk, they compress surrounding clouds, potentially triggering new star formation in the regions they pass. In this way, the death of massive stars indirectly seeds the birth of new ones, continuing the galaxy's long cycle of destruction and renewal. The shells themselves may stretch for hundreds of light years, forming vast arcs that appear as looping, glowing structures when observed in ultraviolet or radio light. Superbubbles also play a significant role in dispersing heavy elements through the galaxy. The shock waves inside them carry enriched material far from the original supernova sites, spreading elements like oxygen, carbon, and iron into the surrounding medium. Over time, this mixing influences the chemistry of future stars and planets. Without superbubbles, the Milky Way would evolve more slowly, its materials remaining confined rather than shared across its structure. Despite their size, superbubbles often go unnoticed in optical wavelengths. They contain little dust and few bright stars, making them appear as empty patches between spiral arms. Only by observing in other parts of the spectrum do their shapes emerge, faint bowls, arcs, loops, and hollows carved into the galaxy's gaseous layer. These structures reveal the dynamic history of the interstellar medium, recording ancient explosions long after their light has faded. If one could float inside a superbubble, the environment would feel astonishingly empty. The density of gas would be lower than almost anywhere in the disk, and the boundaries would be so distant they'd dissolve into faint, glowing arcs. The silence would be immense, not because nothing ever happened there, but because what happened was too powerful, too bright, too violent to leave anything behind except a vast, quiet cavity. Superbubbles remind us that emptiness in the galaxy is rarely accidental. It is often the imprint of brilliant lives ending in spectacular fashion, their final breaths shaping the structure of the Milky Way long after the stars themselves are gone. At the farthest edges of the Milky Way, where starlight becomes sparse and the galaxy's structure fades into a diffuse glow, there exist wandering clusters that drift almost weightlessly through the halo. These are globular clusters, some of the oldest surviving structures in the galaxy, dense spheres packed with hundreds of thousands of tightly bound stars. They glide around the Milky Way in long, slow orbits, tracing enormous loops that can take hundreds of millions of years to complete. Unlike the open clusters found in the spiral arms, globular clusters are ancient relics from the galaxy's earliest days. Their stars formed more than 10 billion years ago, in an era when heavy elements were scarce and the universe was still settling into its long expansion. The low metallicity of their stars reveals their age like faded ink, an unmistakable signature of formation during a simpler time before the galaxy's chemical richness grew through countless cycles of birth and death. A globular cluster's internal structure is astonishing. Stars are packed so densely that in the core, distances between them are dramatically smaller than in the solar neighborhood. If Earth orbited a star inside one of these cores, the night sky would blaze with thousands of bright points, scattered so thickly that darkness would almost vanish. Despite this density, the clusters remain stable, their stars locked together by intense mutual gravity that has preserved their shape for billions of years. Some clusters orbit high above the galactic plane, following tilted paths that cross the disk only occasionally. Others travel in retrograde, moving against the Milky Way spin, evidence that they were once part of smaller galaxies consumed long ago. Their motions carry the memory of past mergers, preserved through time by the gravitational bonds that keep their stars together. When astronomers trace these orbits, they reconstruct the Milky Way's long history of growth, each cluster a silent witness to events now lost to darkness. Globular clusters are not static. Their stars interact gravitationally over long timescales, slowly diffusing toward equilibrium. Heavier stars sink inward, lighter stars drift outward, and some escape entirely, creating faint tidal streams that stretch away from the clusters like delicate threads unraveling into space. These streams help map the gravitational landscape around the galaxy, revealing the influence of dark matter as it subtly bends the paths of escaping stars. Inside the clusters, exotic objects form as a result of the intense stellar crowding. Collisions and close encounters can give rise to blue stragglers, stars that appear younger and hotter than they should, rejuvenated by stellar mergers or the transfer of mass from a companion. Millisecond pulsars, too, are common here. Their rapid spins, driven by interactions over billions of years. These unusual objects make globular clusters laboratories of extreme stellar behavior, places where the usual rules of stellar aging bend in unexpected ways. Some clusters orbit so far from the Milky Way that they barely feel its pull. They linger on the galaxy's outskirts, drifting in regions where the halo thins and intergalactic space begins. These distant clusters, likely formed outside the Milky Way entirely, brought in by ancient collisions that added their stars to our galaxy's growing family. Their loneliness at the edge of the halo gives them a special significance. They are among the faintest, most isolated echoes of the early universe still bound to the Milky Way. If one could look down at the galaxy from great distance, the globular clusters would appear as tiny points circling a vast whirl of stars, each following a distinct looping path. They are not part of the spiral arms, nor the disk, nor the bar. They are guardians of the outer halo, drifting through a realm where time feels stretched, where silence dominates, where their ancient light continues its patient journey across space. Globular clusters remind us that the Milky Way is not only a place of dynamic, ongoing creation, it is also a home to relics, enduring witnesses of a universe that existed long before the galaxy took its present form, each one carrying the memory of stars that have outlived entire cosmic eras. Between the bright structure of the Milky Way's disk and the ancient stillness of the halo lies a faint, almost hidden layer where stars drift with a peculiar quietness. This region is called the thick disk, a subtle component of the galaxy that stretches above and below the main spiral by thousands of light years. It is not as bright as the thin disk where most stars reside, yet not as sparse as the halo. It is the middle territory, a soft bridge between youth and antiquity. The thick disk contains stars that are noticeably older than the ones in the spiral arms. Their chemistry reveals their heritage. Fewer heavy elements, fewer metals, fewer signs of repeated cycles of stellar birth and death. These stars formed early in the Milky Way's evolution, in a time when the galaxy was still assembling its structure. Their presence offers clues about events that took place long before the modern spiral pattern took shape. The thick disk's origin is still debated. One possibility is that it was created when a dwarf galaxy collided with the Milky Way billions of years ago, shaking the thin disk and pushing stars into higher orbits. The collision would have heated the stellar motions, lifting stars above the galactic plane and leaving behind a puffed-up layer thicker than the disk we see today. Another theory suggests that the thick disk formed first during a chaotic, turbulent epoch when gas clouds crashed together rapidly, forming stars in a frenzy before settling into the orderly rotation that defines the thin disk. Whatever its origin, the thick disk carries the signature of a past era. Its stars orbit the galaxy more slowly than those in the thin disk, completing their journeys with a steady, ancient rhythm. Their paths are slightly tilted, slightly oval, and more irregular than the graceful circles traced by younger stars. These motions give the thick disk a gentle, diffuse shape, as though it were a soft version of the disk, blurred through time. Dust is less common here. The thick disk is too old and too high above the dense plain for substantial dust clouds to survive. As a result, the stars glow with relatively unobscured clarity, their light unobstructed by the shadows that weave through the thin disk. This makes the thick disk easier to map in certain wavelengths, revealing patterns of motion and distribution that trace the galaxy's long evolutionary story. Some of the thick disk stars were likely born in the Milky Way, but others may have arrived from outside. Mergers with smaller galaxies would have sprinkled foreign stars into this region, mixing populations from different origins into a single layer. Their chemical fingerprints reflect this diversity, slight differences in metallicity, subtle variations in abundance ratios, hints of environments unlike those in which the Milky Way's native stars formed. The thick disk has a subtle effect on the galaxy as a whole. Its mass helps stabilize the thin disk, providing gravitational support that keeps the spiral structure steady. Without it, the thin disk might warp more severely, twist more dramatically, or respond more chaotically to gravitational disturbances. The The thick disk acts as a buffer, a quiet, stabilizing layer that steadies the Milky Way's rotation. From Earth, most thick disk stars appear faint, blending into the background of the night sky. Only through precise surveys, mapping their velocities, their heights, their chemical compositions, does the structure reveal itself. When plotted on a galactic diagram, the thick disk emerges like a dim, glowing envelope surrounding the brighter disk, a soft halo of stars that holds the memory of the galaxy's youth. If one could drift above the galactic plane and look downward, the thick disk would appear as a wide, faint layer stretching far above the bright arms. It would shimmer with the light of ancient stars, scattered but connected, forming a quiet foundation beneath the halo. It would tell a story of turbulence now long past, preserved in the motion of stars that have been drifting through the Milky Way since the early days of cosmic time. Embedded within the Milky Way's spiral structure is a quiet but powerful influence that subtly sculpts the motion of stars and gas, the galactic bar. This elongated arrangement of densely packed stars stretches across the central region of the galaxy like a glowing spine, guiding material along its length and shaping the flow of matter toward the core. Though invisible to the unaided eye, its presence defines the inner architecture of the Milky Way. The bar is not a rigid object. It rotates slowly, turning once every 100 million years or so, its stars moving along elongated orbits that align with the bar's length. These orbits create a structure that appears solid from afar, yet is composed entirely of stars gliding gracefully past one another. The rotation of the bar influences the motion of gas throughout the inner galaxy, drawing it inward along curved paths that wrap around the bar's edges like streams bending around a stone. As gas flows toward the central regions, it encounters areas of increased density where compression sparks new waves of star formation. Dust lanes trace these zones, forming dark, sinuous streaks that align closely with the bar. The bright clusters and nebulae born along these lanes illuminate the structure, marking the regions where gravitational forces sculpt the interstellar medium into new generations of stars. The bar also interacts with the Milky Way's spiral arms. In many barred galaxies, including our own, the arms emerge from the ends of the bar rather than from the core. This connection creates a smooth transition between the central bulge and the sweeping spirals, guiding the flow of matter from the inner regions into the vast disk. The bar serves as both anchor and bridge, shaping the geometry of the galaxy's arms and helping sustain their long-term structure. Deep within the bar, near its center, the gravitational environment becomes increasingly complex. Here, stars follow tightly looping paths influenced by both the bar's elongated mass and the presence of the supermassive black hole at the core. These orbits are intricate and interwoven, forming a region of high stellar density where interactions occur more frequently. This bustling environment contributes to the ongoing evolution of the central bulge. The bar has also played a key role in the redistribution of material over cosmic time. As it rotates, it exerts gravitational torque on the disk, gradually transferring angular momentum outward. This process allows gas and stars to migrate between different regions of the galaxy. Some stars drift inward toward the bar, joining its flow. Others move outward into the spiral arms. Over billions of years, this subtle exchange has helped shape the Milky Way's overall profile and influenced the development of its structural components. studies of the bar reveal that it is not static. Its length, mass, and rotation speed evolve slowly as the galaxy ages. At times, bars in galaxies can weaken or dissolve, only to reform millions of years later. In the Milky Way, evidence suggests that the bar has grown longer over time, extending farther into the disk as it captured stars from surrounding regions. This extension alters the orbits of nearby stars, producing subtle signatures in their motion that astronomers use to map the bar's present shape. If one could rise above the Milky Way and observe it from a great height, the bar would appear as a bright, elongated core from which the spiral arms unfurl. It would glow more intensely near its center, softening toward its ends, where stars transition into the swirling patterns of the disk. Its rotation would be imperceptibly slow on human timescales, yet its influence would be unmistakable, shaping flows of gas, guiding the paths of stars, and anchoring the galaxy's luminous heart. The galactic bar reminds us that even the quietest structures can have profound influence. Its steady, unhurried rotation has sculpted the Milky Way for billions of years, shaping the grand design of the galaxy without fanfare, without bursts of light, just the gentle, persistent influence of gravity woven through the stars.